Okay, so this is the first lesson of Chapter 7. Chapter 7 is about the trigonometry of right triangles. So I'm going to introduce you to trigonometry. This lesson, I'm going to hope, is going to help you understand what the three primary trigonometric ratios are. So I want you to understand what the three trig ratios are before we can use them. Okay, so hopefully this lesson will help you do that. Okay, so first of all, start off with what is trigonometry. Trigonometry is the branch of math that deals with the relationship between the sides and the angles of triangles. Okay, so for Chapter 7, we're specifically going to be working with right angle triangles. Okay, why study triangles, you might ask? We need to understand trigonometry in order to deal with lots of real-life applications, such as any function that's a wave, circles to calculate distance. Let's say you wanted to find the distance between two of these stars here. Well, you can make a little right angle triangle here. Use trig to help you find the distance of one of these sides. Okay. Sound. Okay. Sound is a wave function. Okay. So we need trig functions to deal with that. Helps deal with motion. Light, as you can see, light can be a wave function. Okay, so many things we need trig for. Okay, so let's start off just quickly reviewing a couple of key principles about right angle triangles. Okay, we know that the sum of all angles in a triangle, so this angle, angle A, plus angle B, plus angle C, that has to add to 180 degrees. Okay, and we know that this little square box here indicates that that is 90 degrees, which makes this a right angle triangle. We also remember Pythagorean's theorem. We'll need this occasionally in this chapter. It tells us that a squared plus b squared equals c squared. So the squares of both of the legs added gives us the square of the hypotenuse. Okay, the hypotenuse, we remember, is the longest side. Okay, so let's just jot that down. The hypotenuse, the longest side. It's always the longest side of a right angle triangle, and it's always right across, it's always opposite to the right angle. Okay, the hypotenuse is always opposite the right angle. Opposite the right angle. The right angle. I use that little angle symbol. Okay? Good, so we're starting to remember about triangles now after we've been working with quadratics for so long. We also need to review some properties of similar triangles. Okay? These triangles, although they're completely different sizes, are similar. They're similar because they have the exact same shape. Okay? They're the exact same shape even though they're different size. I know they're the same shape because they have equivalent angles. Okay? They both have angles of 90, 60, and 30. 90, 60, and 30. So these are similar. They have the exact same shape even though they're different sizes. So there's two properties of similar triangles. They have equal corresponding angles. So angle A is equal to D, C is equal to F, E is equal to E. Okay? They have three pairs of equal angles. Another property of similar triangles, this is going to be important for today, okay? They have equal ratios of corresponding sides. So AC over DF, the ratio of this side to this side, is going to be equivalent to the ratio of this side to this side, and also of BC and EF. The ratio of all those sides is going to be the same. So if AC is twice as big as DF, AB must also be twice as big as DE, and similarly, CB must be twice as big as FE. Okay? So those ratios must all be the same if these triangles are similar. Okay? So, one more thing before we can start with today, we have to know how to label a triangle. Okay? So we need to be able to label its opposite, adjacent, and hypotenuse, those three sides. Okay? So if angle A is our reference angle, we're always going to need a reference angle to be able to label it. Okay? So angle A here is our reference angle. So what side is opposite to angle A? Okay? Well, if I go right across, opposite from A, okay, the opposite side is BC. I know the hypotenuse The hypotenuse is always, always, always side across from the right angle. Okay? Side opposite the right angle is the hypotenuse. So BA is the hypotenuse. It's opposite of C. It's also the longest side. Okay? Adjacent means, that's a fancy word for beside. So what angle is adjacent to this angle A? Right here, side AC is right beside it. That's the adjacent one. So if angle A is our reference angle, the hypotenuse is always across from the right angle. The opposite side to angle A, we go across the triangle. There's the opposite side, adjacent, right beside the angle. Okay? Now, what if our reference angle changes? So what if our reference angle is now B? Okay? Our hypotenuse doesn't change. Our hypotenuse is always across from the right angle. So if this is our right angle here, our hypotenuse doesn't change. That's all. Hypotenuse is always across from the right angle, right opposite to it. And it's always the longest side. Okay? But what's going to change now, the side opposite to angle B, if we go across the triangle, opposite to angle B is right here. So AC is now the opposite. And the side beside angle B, so right adjacent to it, would be side BC. Okay? So that's how we label a triangle. We label its opposite, adjacent, and hypotenuse. Okay? And it all depends on where our reference angle is. Okay? Our reference angle is always going to be one of the two non-90-degree angles. Okay? Good. So I'm just going to show you a quick demonstration using GSP about some similar triangles and how we're going to discover these trig ratios. Okay, that we're gonna figure out. Okay. So what I've made here are two similar triangles. Okay. You can tell. I'll just label the angles here. Okay. So for this triangle here, for triangle ABC, angle B is our 90-degree angle. Okay. Angle A, I've said is 48.35, 48.35, and angle C is 41.65. Okay. And over here, this is a similar triangle. I know that because it has the exact same angles. That means it's the same shape, even though it's a different size. Okay. So angle E is 48.35. Okay. So that's the same as angle A was, and angle F is 41.65. Okay, good. So you can tell these are similar triangles because they have the exact same angles. Okay, even though they're different sizes. Okay, we should also remember that similar triangles don't only have equal sides; they also have equal ratios of corresponding sides. Okay, so if I take a look at the ratio of, hold on, we're just going to do a little discovery here. Okay, so if I make angle C my reference angle, okay, so that would make angle F my reference angle for this one, so I keep it the same because angle C is equal to angle F. They're both the same. So if those are my reference angles, this would be my opposite side, opposite that angle. This would be my hypotenuse, the side across from the right angle, and this would be the adjacent side, the side adjacent to that angle. Let's label this one, opposite to angle F, adjacent to angle F, and here's my hypotenuse. Okay. So what I'm going to be interested in now to figure out these trig ratios, let's look at the ratio of the opposite to the hypotenuse for both triangles. So if I do opposite over hypotenuse for this triangle, if I do 8.81 divided by 13.26, let's see what we get. Let's put that in our trusty calculator. So if I do 8.81 divided by 13.26, I get 0.6644. So that gives me 0.66. Okay. Now let's see what the ratio of the opposite to the hypotenuse is for this triangle. So if I do 5.53 divided by 8.32, let's see if that ratio is the same. Let's see if that works. 5.53 divided by 8.32. It does. I get 0.66 for that as well. Okay? So I did opposite over hypotenuse for both of these. So I did opposite over hypotenuse for both of those. And I found that even though these are totally different sized triangles, because they're similar, that means these triangles are directly proportional to each other. Okay? So that's what makes these ratios exactly the same. The ratio of the opposites of the hypotenuse for this triangle is exactly the same as the ratio of the opposites of the hypotenuse for this triangle. Okay? That ratio is called the sine ratio. Sine is opposite over hypotenuse. Okay, that's the sine ratio. There are two other ratios. Because we have, let me just open up our lesson again here. Because we have three different pairs of sides. Okay? So if I look at this triangle here, I could look at the ratio of the, let me just get my highlighter out here. I could look at the ratio of the opposite over the hypotenuse, which is what we just did, and we knew that was, we called that the sine ratio. I could also look at the ratio of the adjacent over the hypotenuse. That would be another ratio I could look at. That's called the cosine ratio. Or I could look at the ratio of the opposite side to the adjacent side. That's called the tan ratio, tangent ratio. Okay? So those are the three different combinations of sides we can have. So we can look at the ratio of all of those. And what we've discovered, okay, for similar triangles, okay, let's just look at this bottom part first right now, okay? For similar triangles, even though the lengths of the sides may change, the measures of the angles do not change, okay? So these triangles that we looked at were similar. These were similar. Even though the lengths of the sides were different, we know they're similar because they have equivalent angles. The angles are exactly the same, okay? And we discovered that the ratio of the corresponding sides doesn't change. Okay, so the relationship stays the same. The opposite over the hypotenuse was exactly the same for both the triangles because they were similar. Okay, because they had exactly the same angles, their proportions were the same. So opposite over the hypotenuse was the same for both triangles that had an angle of 41.65. Okay, so like I was saying before, each triangle has its own unique sine, cosine, and tan ratio. There's three ratios. The sine ratio is the opposite over hypotenuse, what we looked at. Cosine is adjacent over hypotenuse, and tan is opposite over adjacent. Okay, so why is this important? So from the investigation that we did on GSP, okay, we know the sine ratio from an angle of 41.65 should be 0.66. Okay, the ratio, if we have a 41.65 degree angle in there, the ratio of the opposite side to the hypotenuse should be 0.66 for all right angle triangles with a reference angle of 41.65. Because all right angle triangles with an angle of 41.65 are similar triangles, because all three of those angles would have to be equal. Okay, so all of their ratios, opposite over hypotenuse, should be 0.66. So we could use that ratio to solve for a missing side. If we know the angle in here, 41.65, we know the ratio of opposite over hypotenuse, x over 6, should be 0.66. Okay, so we know x over 6, oh, I don't want highlighter. We know x over 6 should be equal to 0.66. Okay, so we could solve for x. Just multiply 0.66 by 6. Okay, so we know that. Will we have to memorize the ratios for all the possible angles? Like, yeah, okay, we figured this one out, 0.66, by doing that GSP demonstration. Are we going to have to memorize all of these? No, your calculator has stored all of these for you. Like, on your calculator, if you put in the sine oh, turn on first. If you put in the sine of 41.65, press enter. Oh, what did I do here? If you put in sine of 41.65, oh, I'm not on degree mode. That'll change it. Make sure, there's a good lesson for you. Make sure your calculator is on degrees. We don't know anything about radians yet, okay? So sine of 41.65, hopefully it gives us 0.66, and it sure does, okay? So every triangle with an angle, every right angle triangle with an angle of 41.65 will have a ratio, a sine ratio of 0.66, okay? Sine being opposite over hypotenuse, okay? So this is the same because each angle has a unique sine ratio that never changes, okay? So what I want to take away from this, the fact that there are three ratios, and if we know a right angle triangle has an angle of theta, okay, if we know the angle, we know all other right triangles with that same angle are similar, and therefore have equivalent ratios, okay? Those ratios are the same for all similar triangles. Let me just show you one more GSP sketch quickly, just to demonstrate that one more time. Let's see if I can get it open here. Okay, so here we go here. I've got a right angle triangle here. Okay, angle C is at 90 degrees, so angle ACB is at 90 degrees. My angle B is 51, and my angle A is at 38. Okay, you'll see I've got set up here the sine ratio, cosine ratio, and tan ratio. Okay, from angle B. Okay, so angle B is 51.5, and these are the ratios from that reference angle. And here's the length of each of the sides. So you'll see, if I change the angle, so you'll see these angles start to change, you'll see that the sine, cosine, and tan ratios also change. So if the angle changes, you'll see the trig ratios also start to change. Okay? But if I only change the size of this triangle and don't affect the angles, okay, I'm not changing the angles, I'm just affecting the size. See, the angles are staying the same. The trig ratios also stay the same. Okay, because for all similar triangles, the trig ratios are the exact same. So if the reference angle stays at 51.34, angle B isn't changing, the sine, cosine, tan ratios are the same for all of these triangles that I'm making right here. Okay? So no matter what size it is, the trig ratios stay the same as long as the angles are staying the same. Because each angle has its own unique sine, cosine, tan. But as soon as the angle starts to change, the trig ratios also start to change. Okay? Hopefully that helps us understand a little bit how we can use, or why we can use these trig ratios. Okay? Here's an acronym you can use to help you memorize it. Okay? The trig ratios. Sine is equal to opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. And you can say this as SOH CAH. SOH CAH. SOH, sine, opposite over hypotenuse. CAH, cosine, adjacent over hypotenuse. TOA, tangent is opposite over adjacent. Okay, so let's put this into action a little bit. Let's do this quickly. Up to this point, it's just been kind of an understanding thing. Now we'll actually use these. Okay, so find the following trig ratios. If this is my triangle, here's my reference angle right here. And it's going to ask me to find the sine of theta. Okay, theta is the Greek symbol we're going to use to identify an unknown angle. Okay, so the sine of theta, we know sine is opposite over hypotenuse. Okay, so opposite is right here, and my hypotenuse is across from the right angle, so it's right there. So sine of theta is opposite over hypotenuse is 12 over 13. If I do 12 over 13, I should get 0.998. No, 92. 0.92. Okay? 0.92. Cos of theta is adjacent over hypotenuse. Okay, adjacent over hypotenuse is cosine. So this is my adjacent side to theta. Okay, this side here, side of 5, is right beside my reference angle. That's why it's the adjacent. So cosine of theta is 5 over 13, adjacent over hypotenuse. 5 divided by 13 is close to 0.4. It's 0.38. Okay, now I have to find tan. That's my last ratio. I know tan is opposite over adjacent. So opposite over adjacent is 12 over 5. That'll give me a nice round number of 2.4. Okay, 5 goes into 12, 2.4 times. Okay, let's do one more example. Make sure we're good with this. So if this is our reference angle here, right here, and I want to find the 3 trig ratios for this triangle, what you might want to get in the habit of doing first is just labeling your opposite side right across from theta, your adjacent side right next to theta. Oh, I almost started labeling that hypotenuse. Adjacent side, and your hypotenuse is across from the right angle. There it is. Okay, so sine of theta, if I remember, sine, so, is SOH over H, sine opposite over hypotenuse. So opposite over hypotenuse is 5.8 over 11.1. That is 0.52. You'd have to put that one in on your calculator. Okay. Cosine, CAH, is adjacent over hypotenuse. Okay. So adjacent over hypotenuse is 9.5 over 11.1. Over 11.1. On my calculator, that gives me 0.86. Okay. Tan, TOA. Tan is opposite over adjacent. So that gives me 5.8 over 9.5. 5.8 over 9.5. And that's equal to 0.61. Okay, that's it for today. Hopefully you understand why we can use these ratios. Okay, because every triangle that has the same reference angle is going to have this exact same ratio. Okay, hopefully we remember that. Just make sure you have, this is the important slide here. It goes through everything, shows you the 3 ratios, and it tells you here if we know an angle has, we know the reference angle, we know all other triangles, right angle triangles, sorry, with that reference angle, have equivalent sine, cosine, tan ratios, because similar triangles all have the same ratios of these sides. Okay, so hopefully that helps. Let me know if you have any questions. See you guys.